Section 3, Electromagnetic Forces, page 96. If you're using a compass to find north, be sure that no one holds an electronic device near the compass. Electronic devices can change the direction compasses point to. Why does this happen? Electronic devices interfere with compasses because the devices cause magnetic blank, number 1. However, these magnetic fields are not caused by magnets. Instead, the magnetic fields are caused by moving particles with an electric blank, number 2. Charged particles move as electric currents in the device's circuits, as you learned in the previous lesson. Can you predict how a magnetic field created by a current will affect blank, number 3? On the left in figure 3a, the wire in the center of the compasses does not carry a current. So there's 6 compasses and a wire that runs right down the center. Because no magnetic field surrounds the wire, there is no effect on the compasses. All the needles point north to align with Earth's magnetic field. However, when the wire carries a current, there is an effect on the compass as seen on the right in figure 3a. The compass needles align with the stronger magnetic field caused by the blank, number 4. The needles form a circle lining up with the magnetic field around the wire. Here's the text for figure 3a. Moving electric charges can cause a magnetic blank, number 5. The compass needles in the image on the left all point north because of Earth's magnetic field. But when the wire carries a current, the current causes a magnetic field around the wire, and the compass needles turn to align with that field. The compass needles are turned by magnetic forces caused by the electric blank, number 6. The magnetic forces caused by an electric current are one kind of electromagnetic forces. Another kind of electromagnetic force is the force on electric charges caused by a changing magnetic field. How can a magnetic field change? You can change the magnetic field around charges in a wire in 2 ways. You can either move a magnet near the wire, or you can move the wire near a blank, number 7. Either way, the electromagnetic forces on the charges in the wire cause the charges to move and form a blank, number 7. The electromagnetic forces from a current-carrying wire are strong enough to move the compass needles. The forces can be made stronger by forming loops to make a coil out of the wire, as seen in figure 3b. The more loops formed in the coil, the stronger the magnetic forces exerted by the blank, number 8. The forces can be made even stronger by wrapping the current-carrying wire around a piece of iron. Next page. This is the text for underneath figure 3b. The electromagnetic forces exerted by a current-carrying wire can be strengthened by forming loops to make a coil. Increasing the number of loops in the coil increases the wire's electromagnetic blank, number 9. The text for figure 3b, the electromagnetic in the photo can be turned on and off by turning the current on and off. The property of electromagnets make them useful for moving metal objects, just like we did in class. A magnet made with a current-carrying wire, that's what you had yesterday, was a current-carrying wire, whose strength can be varied and turned on and off, is called an electromagnet. A couple of you asked me if you would have connected 2 batteries together, would our current have been stronger, would our magnet have been stronger, and it would have depended upon how we connected the batteries. A magnet made with a current-carrying wire, whose strength can be varied and turned on and off, is called an electromagnet. Electromagnets are different from refrigerator magnets and other magnets you use in everyday life. Refrigerator magnets and other everyday magnets are called permanent blank, number 10. A permanent magnet is a magnet that is always surrounded by its magnetic field. It's permanent. Electromagnets differ from permanent magnets in several ways. First, electromagnets can be turned on and off. Second, the strength of an electromagnetic force can be changed by changing the amount of current in the wire or by changing the number of loops in the blank, number 11. Third, an electromagnetic pole can be blank, number 12. The direction the current travels determines which end of the electromagnet is the north pole and which is the south pole. If the current's direction is switched by switching the wires on a battery or by rewiring the circuit, the poles of the electromagnetic switch blank, number 13. The properties of electromagnets make them useful in industry. For example, an electromagnet can be used to move metal objects in junkyards. A current-carrying wire is wrapped around an iron core, increasing the magnetic forces of the blank, number 14. The electromagnet is turned on, and a magnetic force lifts the objects. A crane moves the electromagnet and the objects to a different location. Once the electromagnet is turned off, the objects are no longer attracted to the electromagnet and will fall into a new blank, 15. Real quick, let's look at the 3 questions. What causes the magnetic fields in electronic devices? Number 2, what are 2 kinds of electromagnetic forces? And then number 3, probably the most important one, explain the difference between an electromagnet and a permanent magnet.